Yes. But okay, okay. Can you make a little bigger? Okay, it's okay. Okay, it's okay. Thank you.
Um, Great. Uh, Sorry. Great. Okay. Okay. So now it's working for me. Right. So, okay. Munich Center for Mathematical Philosophy. Um, I work in philosophy of physics, mostly philosophy of science generally, and I use a lot of categories in my work. Um, uh, when Marcelo asked me to give this presentation, I thought that I would give a very broad introduction to some of the uses that people have put category theory to in philosophy of science right now. So before I start, I'd like to say thank you both to Marcelo for organizing this and for having me speak, and also to Daniel for helping with all of the technical issues, and of course all of the other organizers for their help. Um, is there a problem? Ah, great. Okay, thanks. uh, Good. Okay, so I'm glad that got fixed. Okay, so right. So today there's about 2.5 hours worth of time. Um, in that time, I thought I would do two main things. For the first part, I would say something very, very, very broadly about formal philosophy of science. So I assume some people here will have encountered formal philosophy of science before, but because the description from that Marcelo gave me was that the goal of this initiative is for introducing philosophy of mathematics to young mathematicians, and so I thought that meant that the audience would be very more on the mathematics side, and also with maybe not because younger, would be helpful to have more background. So I'll talk about that for a while, and then because this is online, I thought it'd be nice to take a short break in the middle. We can do some questions if there are some, and then maybe take a moment to stand up or so. And then in the second half, I'll say something more about category theory in particular in philosophy of science, and about some sort of contemporary research questions, and get near the end towards some of the stuff that I work on. Right. So good. As I said, the sort of expected audience for this talk is that you're going to have no background in philosophy of science. So if you do have some background in philosophy of science, you might think some of this stuff is very basic. But I'm also going to assume that you have some interest in philosophy of science. And so I'm not going to spend a lot of time trying to justify or explain interest in philosophical questions, but rather to say, if you're interested in philosophical questions, here's why you might also be interested in using category theory in philosophy of science. Because the audience was meant to be mathematically interested and skilled people, I'm going to assume that people have some experience with mathematics, but not a ton. And I will be primarily focused on philosophy in this talk. So the general goal of the talk is to convey some idea of one connection between category theory and philosophy of science, and then give you at the end two examples of category theory applied in philosophy of science within this sort of broad context for connection, and then at the end perhaps some specific philosophical questions to think about further. So in light of this expected audience and intended goals, I'm going to say that there's going to be more focus on philosophy than on mathematics in what I'll say. And there'll also be something of a long philosophical setup. So I'm going to start pretty far back in the early 20th, I'll say mid 20th century. And then the first part is going to be a lot of context setup for how could category theory ever have anything to do with philosophy of science? Well, here's kind of the context for that. Okay, so then I'll get started. So the starting point is with one of the basic concepts of Anglophone philosophy of science in the 20th century. Philosophers of science often think of themselves as studying theories, in much the same way that philosophers of art think about themselves as studying artworks, or philosophers of language think about themselves as studying languages. Philosophers of science think about themselves as studying scientific theories. And this notion of a theory is, I think a relatively everyday one, at least at first, right? So there's the theory of quantum mechanics, and there's the theory of general relativity, and there's the Newtonian theory of gravitation, and things like this. But when one talks about these different theories in more detail, then you need to do a little bit of approximation or idealization. Think about, what exactly counts as being part of the theory and not part of the theory. And roughly speaking, the way that philosophers of science use the idea of a theory is that it's something like a snapshot of a scientific field. So it's not necessarily something that any one person believes or asserts or anything like this, nor is it usually something that evolves over time. You can talk about evolution over time by talking about theories at different times and connecting them, but usually the way that philosophers of science tend to talk about theories, they are these sort of self-standing things that are abstracted away from actual scientists who build these kinds of things, right? So a scientific theory in the philosopher of science's use is something like a summary of textbooks and journal articles and conversations at the water cooler, this kind of thing. So it's a somewhat self-standing and abstracted kind of notion. Once we have our hands on this notion of a particular theory, there's various questions that philosophers of science like to ask. So, for example, how is a theory supported by evidence? Now, sometimes philosophers really are interested in a particular theory. How is this theory supported by evidence? And I think that this usually happens when there's some kind of philosophical question in that theory itself. So one long-standing question is, how exactly does the evidence support quantum mechanics, right? Which parts of quantum mechanics are supported by which evidence? And this is a question that philosophers of science often concern themselves with, because there's philosophical questions about what quantum mechanics says about the world. And so they want to understand, well, which parts of the theory are better supported by evidence and which parts are less supported by evidence. There was also, in the early days of general relativity and the geometrization of gravity, a similar kind of question about how exactly should we understand the relationship between convention, evidence, geometry, and gravitation. So these kinds of things. So that's the kind of question that a philosopher of physics will tend to spend a lot of their time with, looking at a particular theory and asking, how are the different pieces of this theory supported by different bits of evidence? But in general philosophy of science, people are usually, at least in the context I'll be talking about, people are usually looking for a general theory about the relation between theory and evidence. And so the question isn't necessarily how is that theory supported by evidence, but rather, in general, how does one support a theory using evidence? And so you might see, in order to answer that kind of question, you need to have this notion of like a theory that is sort of out there. It can be related to evidence that's also out there. And you have to ask, how are the parts of the theory? How are they related to the evidence? This kind of thing. And so this is why I said we need this kind of snapshot of this, it's a pretty somewhat abstract, very idealized notion of a theory. Okay, so there's some other questions that I'll go through a little bit more quickly. One is, what's involved in accepting a theory? So, people, if you ask physicists, they'll usually say things like, well, Einstein gravitation is the accepted theory of gravitation right now. Newtonian gravitation used to be the accepted version. Depending on how they like to talk, they'll either say, well, Newtonian gravitation isn't really accepted anymore. It's not the full, we think that there are regimes where it breaks down. We think that in those regimes one has to use Einstein gravity, and that in regimes where Newtonian mechanics is basically right, that's because it agrees with Einstein gravity. And philosophers of science will often say that, well, if you accept that some theory is true, then you also accept what it says about unobservable things. And so one of the more controversial cases of this was in debates over the atomic theory of matter. This theory seems to say that matter, gas, these things are made out of unobservable particles. And because they were unobservable, various empiricist philosophers thought that that made them kind of scientifically not respectable. And so the question was, is it possible to kind of accept the atomic theory of matter and accept what it tells us about boxes of gas and other things without accepting that molecules exist? And so this is one way into what's a debate about what's called scientific realism. Another question, how do theories explain the phenomena that they are about? So this is usually going to be some story about how different parts of the theory are related to each other and to the phenomenon. What's the epistemic status of different parts of the theory? Some of it you might think we know, some of it we might think is a guess. How can we figure out which parts are justified and which ones are less justified? This is related to the first question about how you support a theory using evidence. Okay, the rest, how should we understand certain concepts appearing in the theory, especially in things like quantum mechanics? How should we understand, say, the probabilities that come up in quantum mechanics, this kind of thing? How do the claims of the theory relate to the real world, especially in cases where we have, say, a theory with heavy approximation or idealization? How do we understand what is involved in idealization, right? We don't think that the world is really exactly like the idealized theory says, but we think that the idealized theory is getting something right. How can we spell out this notion of getting something right in a not exactly literal sense? And then another question people like to ask is what makes one theory successful and another unsuccessful? To some extent, this is going to be one of them gets the empirical stuff right and the other one doesn't. But even when you have two theories with the same empirical content, you might think one could be more successful than another. So the thing that I wanted to show by listing all of these typical questions is that they all involve the notion of theory. And so the starting point to answer many of them is to say, well, we need to have some idea of what a scientific theory is if we're even going to get started. Now, in about, let's say, 1920, this is one of those things where, like, you could start earlier, you could start later. I'm going to pick about 1920 because that's when there's this book by Campbell that picks this out. Oh, I should also say, because this is meant to be a kind of invitation to category theory, formal philosophy of science, there's a relatively long list of references at the end of this talk. So if you downloaded it using the QR code on the first page, that you have access to that. Otherwise, please feel free to email me if you would like the slides and the references. But okay, so we want to know what a scientific theory is so that we can approach many of the questions that are asked in philosophy of science. There's, in, say, the 1920s or so, there was an orthodox view about what a theory is that was by and large accepted by most people. And according to this view, a theory is a formal system of definitions and postulates. The theory says there are these things. I'll take the atomic theory, for example. The theory says there are these things called molecules, and they make up gases, and they behave according to the laws of Newtonian mechanics. And from these laws of Newtonian mechanics, along with, say, the rules of probability or something like this, you can derive various predictions. And this is essentially, I mean, thought of as essentially a mathematical theory. We've got some axioms, and we can derive things from this. What counts as being true according to the theory is what you can prove using these postulates. And so the theory says, you know, there are these molecules that behave this way. That implies that this box of gas will behave in such and such a way. And so according to the theory, that's what will happen. The theory says, yes, it's true that this box will cool down in this context. And then what you ask is, okay, well, is this theory right? You know, the theory says that's true, but is it really true? How do you figure this out? Well, what you need to do is you need to take the formal system that is the theory and come up with a way of, say, tying it to the world or coordinating it with the world. And in the orthodox view, the way that you do this is you say certain pieces of the theory match up with certain pieces of the world. So there are certain concepts that appear in the theory that match up with empirical concepts, things that are available to observation. And then once we have this connection, we can make derivations in the theory to some claims about these concepts in the theory that are coordinated with the world, and then use that coordination to make claims about the world. And so once you set up the coordination, the theory is going to explain general empirical claims by deriving them from the postulates. And the theory is successful if the empirical claims that it implies are true, right? So we've got this sort of general system. I have a picture on it 2 slides from now, but I'll just say this now. There's a kind of 3-layer structure here. At the highest level, there's this abstract formal system of definitions and postulates. From this system of definitions and postulates, one derives various general claims. These claims are then coordinated with what's going on in the world, and then that implies certain specific empirical claims. And the idea is that you explain things that you know by showing how they follow from the theory, and you predict things that you don't know by showing that they would follow from the theory in the situation you're interested in. Okay, so I said a theory is a formal system of definitions and postulates. What does this mean in practice? Well, it means the same thing it means in mathematics, basically. So that's meant to be, that's the intended analogy anyway. So here's an analogy of group theory, right? This is a theory, you might say, of a certain kind of mathematical object, a group. This is a set, G. It's equipped with a function with 2 arguments and an element, E, such that these 3 postulates are, or axioms, or conditions are satisfied. Multiplication is associative, E is a unit for the multiplication, and inverses exist. So the thought is, according to the orthodox view, a scientific theory is just a more complicated version of something like this. We begin here by saying, well, there's this set, there's a function, there's an element, just so, there's a collection of molecules, these molecules have certain properties, these properties interact in a certain way. Here's some examples of groups. The integers are equipped with addition, the automorphisms of some object equipped with composition, or if you studied some algebraic topology, homotopy classes of pointed maps from the n-sphere to some space equipped with concatenation. Now, the thing that is supposed to be similar about scientific theories and mathematical theories is that as far as the theory of groups is concerned, an inverse is anything that plays the right role, right? So what's the right role? It's the thing from the previous slide. It's whatever the element is such that interacts with multiplication and the identity in this way. In much the same way, when I said that a theory is a formal system, the thing that people are intending to say by this, or one thing that the orthodox view is intending to say by this, is that all there is to the concepts in the theory is the structure that they exhibit. And so if you want to ask something like, what is a molecule? The only answer you can give in the orthodox view of theories is, well, it's the kind of thing that behaves in this way and that interacts with other molecules in that way. Right, what more do you want? An analogy that was very often used at the time to explain the sense in which the theory is meant to be a formal system, uninterpreted, that requires coordination, is geometry. So here's an informal presentation of hyperbolic geometry. There are these things called points, lines, circles, and angles. They satisfy the following properties. A line can be drawn from any point to any point. Any line can be extended indefinitely. Around any point, there's a circle of any radius. All right angles are equal. And for any line L and point P not on that line, there are at least 2 distinct lines through P that do not meet L. So you might recognize, of course, the first 4 of these are shared with Euclidean geometry, and the 5th is different from Euclidean geometry, which says there's exactly 1 distinct line that does not meet P. Here's a picture that you've probably seen from Escher of the Poincaré disk, or of a model in Euclidean geometry of hyperbolic geometry. Now, the sense in which this is a model of hyperbolic geometry is that if you think of the points in this disk as points, and you think of the white curves, I think you can see my cursor. You think of these white curves as lines, then all of the postulates in the theory are going to be satisfied by this illustration. But now you might say, if you've not encountered this kind of thing before, hold on, John, you said there are points, lines, circles, and angles, and so forth, and they satisfy these properties. But in what sense are these white curves lines? They're curved, not straight, right? This is exactly what is meant by the sort of formality of the axioms. If you look at these 5 conditions and you interpret line as white curve, then you'll find all 5 of them are true in this disk. And that's really all there is to say, right? And so there's a kind of informal interpretation of points, lines, etc., that's not going to match this more concrete interpretation in terms of Euclidean geometry. This isn't really a problem. This is just an illustration of the fact that you need to be careful to separate the meaning of terms sort of pre-theoretically and the meaning of terms as they occur in the theory, right? So, of course, you know, you're mathematicians, and so you're probably very well familiar with this kind of thing, but this is something that is one of the more controversial pieces of the orthodox picture of theories. That when it comes to the concepts of a scientific theory, all there is to say about their meaning is the role that they play in the theory until you coordinate them somehow with the world, and then you can say a little bit more about how they attach to the world, right? So this is a picture of the orthodox view from this paper by Feigl in 1970, defending the orthodox view. And as I mentioned before, you have this 3-layer structure. Up here are the postulates and the primitive concepts that they relate. There's then a middle layer of defined concepts that can be defined using the resources of the theory. And then these defined concepts are coordinated with empirical concepts, which we come to understand and have before or without the theory. And then these empirical concepts are related to, as Feigl puts it, the soil of observation, which is experience. And so there's a kind of formal meaning that we can give to the primitive concepts and the postulates, which is just the interrelation. But if you want to have something that goes beyond a mere formal meaning, you have to connect them somehow to reality or experience or observation. And then to some extent, the meaning that we get from the kind of usual understanding we have of observation will percolate up to the rest of the structure. Okay, so that's really broadly speaking what I've been calling the orthodox view of theories. This is a starting point in the sense that it's not generally accepted anymore. It was generally accepted. It is the kind of thing that seems, at least to a first approximation, rather plausible. And yet, since 1920, so I guess the last 100 years or so, you know, it's been pretty steadily criticized. And to the extent that people still think it gets something right, they think that there's going to be a lot of modifications that are required to fix it, to make it into something plausible. So in order to say something about, you know, what we can still say about the orthodox view of theories now, it's helpful to look at a particular thread of this debate. So there's very many criticisms that people have leveled against this way of thinking about theories, but I think there's one that's particularly helpful in understanding how you might use category theory in philosophy of science today. And that framing controversy is the problem of scientific realism. And here's how you can sort of get this. Here's how this question comes up in the orthodox view. Theories are only partially coordinated with observation. So this is, I attempted to emphasize earlier that there's, at the top level of the theory, the thing floating way up there, there's interactions among the postulates and the definitions, but there's no connection to observation, except via this intermediate level of derived concepts. And so there's going to be some parts of your theory that are coordinated directly with observation. There's going to be some parts that aren't. Call this part the unobservable part. This part is going to usually include things like molecules. So in the atomic theory, one says, there are these things, they are molecules. You cannot observe them. There are things called boxes of gas. You can observe these. there's a particular relationship between boxes of gas and molecules, namely boxes of gas contain a whole bunch of molecules, so many that we can study them using the tools of statistical reasoning and Newtonian mechanics. But then there's this question, do molecules exist? I wrote, do these observables exist? I should have written, do these unobservables exist? Sorry for that typo. The controversial thing is, do the unobservables exist? Everybody says, yes, I believe that boxes of gas exist. Should I also believe that molecules exist? And roughly speaking, there's two kinds of answers here, at least that were live at, say, the 1920s and 30s. The realist answer, which says, yes, the molecules really exist. The unobservable things, the stuff that isn't directly connected to observation, does indeed exist. The instrumentalist answer says, I don't even know what you're asking. I don't know what it would mean for molecules to exist because I don't know what molecules are except for the role that they play in the theory. Right, so to say this again in more detail with the kinetic theory of gases again, the theory, right, is a collection of postulates and concepts and definitions. It says something like, there are these Newtonian particles, we have a term for them, that term is molecule. The separation between these particles is large compared to their size. The number of particles and the volume that they occupy is large. They interact only through elastic uncorrelated binary collisions. So this can be spelled out in more detail and rigor such that you can actually turn these into mathematical claims and make, you can prove things about it. But insofar as we're thinking of this as a theory in the orthodox view, we haven't actually said anything about physics. We haven't said anything about nature or the world or observation. We've used terms that sound like everyday terms like particles and collisions and so forth. But the thing that the orthodox view wants to emphasize is that we have to be careful not to make the mistake that people sometimes make when talking about hyperbolic geometry. We don't want to make the mistake of associating other things with these concepts that were not part of the formal theory. If we want to associate the formal theory with the world, we need to explicitly coordinate some parts of the theory with the world. What we do in the case of the kinetic theory of gases is to say, certain systems of these particles get coordinated with boxes of gas. And when we make a particular system coordinated with a box of gas, then the temperature of that gas is going to be proportional to the average kinetic energy of that system of particles. The pressure of that gas is the force exerted by the particles on the walls of the box. Temperature and pressure, let's say, are the kinds of things that you can observe or measure. Systems of particles are things that you can talk about in the theory, right? They aren't basic concepts. They aren't parts. I mean, the system of particles itself is not one of the postulates. Rather, you postulate there are particles, and then you say, well, let's think of a particular, define a system of particles to be, a certain volume that contains particles of 10 to the 23 or whatever. So when we have this kind of coordination, we can coordinate the system of particles with a box of gas, but we can't coordinate an individual molecule with anything, because there's nothing in observation that is an individual molecule. So I think I've got, a little picture here, right? So this is, roughly speaking, the kind of picture that one has when one talks about the kinetic theory of gases. We have this box of gas, it's split in two, side A and side B. It's separated by a little door. At the beginning of the experiment, we have all of the blue molecules on one side, all the red molecules on the other. When you open the door, they then, permeate each other. You can explain, say, temperature gradients. You can explain pressure changes, these kinds of things, using statistical reasoning about particles, and then coordinating that statistical reasoning with observational features of gases. Much like the hyperbolic geometry example, one has to be careful here not to think that molecules are little blue balls or little red balls. Molecules don't have colors. Molecules aren't actually physical things on the orthodox view of theories. Or rather, one doesn't know what it would mean to say that molecules are physical things. Right? A molecule is whatever it is that plays the role that's in the theory. And that's just a role that's not something that's related to the world, it's something that's related to other parts of the theory. You know what a box of gas is, and you know what a system of molecules is, and so according to the theory, you can see systems of molecules and experience various features of those, but individual molecules themselves, you can't. And so this picture is misleading in much the same way that the hyperbolic geometry picture was misleading. This adds in a whole bunch of features that aren't part of the theory and which make it seem like, oh, there are these molecules in addition to the boxes of gas, when according to the orthodox view, there are not. So, to repeat myself, I guess, asking whether, according to the instrumentalist view of theories, asking whether there are really molecules is like asking whether lines in hyperbolic geometry are really curved. And I said before, that's kind of the wrong question to ask, right? Because in a model, we might say, well, there's a sense in which in that circle 3 model, the lines in hyperbolic geometry are curved. They're curved according to Euclidean standards, but that's just not part of the theory. We're only able to say that once you coordinate the formal theory of hyperbolic geometry with a concrete Euclidean model. But it's actually worse than that in the case of scientific theories. In the case of the hyperbolic geometry, we can say that, well, circle limit 3, this Escher picture, interprets hyperbolic lines as Euclidean curves. And so we should be careful to keep track of whether we're talking about the Euclidean features or the hyperbolic features. In the case of the orthodox view of theories, the term molecule actually isn't interpreted by anything. There's nothing in the observation or physics that counts as the thing that interprets the term molecule. We interpret the term system of molecules, but not individual molecules. And so asking whether there are really molecules just isn't really a question, right? That's like, because asking, are there really blahs, is asking, there's a certain kind of thing, blah, are there really ones out there? But molecule isn't the kind of thing. It's not a term that we can make any sense of, except within the context of a theory. And when you're in the context of a theory, it does mean something. And what it means is a certain formal position in the theory, according to which various other bits of the theory can be related. And so really asking whether there are molecules just doesn't really make sense. You can ask whether talking about molecules helps us to neatly organize the generalizations about things we've observed. You can ask whether it's a useful way of speaking to talk about molecules, but that's like the closest you can get to asking whether there are really molecules. Okay, so that's then the kind of realism problematic in the case of the orthodox view of theories. We've got a picture about what a scientific theory is. In that picture, there's certain kinds of questions that make sense to ask and certain ones that don't. The scientific realist is somebody that thinks, well, there really should be a way to ask whether molecules exist. And because the kinetic theory of gases is so successful, I should be able to say that's evidence that molecules really exist. But if you really hold on to this orthodox picture about what a scientific theory is, then you're going to say, you know, that just sounds like nonsense to me, really, right? You're asking, if you're careful, you'll see that that sentence just doesn't make sense. So if you want to be a scientific realist, as various people did, you're going to have to criticize that picture of theories, because that picture of theories prevents you from asking the kinds of questions or asserting the kinds of things that you would like to assert. And there were extensive criticisms of the orthodox view of theories. There are too many for me to talk about all of them, or even to put all of them on a slide, but let me very briefly allude to a couple. So one criticism that you might associate with Feyerabend or Sellers, Wilfrid Sellers, Paul Feyerabend, is that this notion of observation with no theory involved is just mythical, right? When we look around, we see things like a laptop, a glass of water, a mug, a radiator, and things like laptop and radiator, if you really are careful, you'll see are concepts that we had to develop. You can't know what a laptop is without knowing something about the theory of electricity. And because of this, there's no way you're going to be able to talk about observation really without using terms from a theory. And so there's not going to be this sharp distinction between the theory up top and the observation down low. At best, there'll be kind of a gradient. And Feyerabend, for example, thinks there's not even that, really. Because of this, you can't have this sharp instrumentalist distinction between the stuff that it makes sense to talk about existing and the stuff that you can't. This is a way to sort of, get realism back on the table. Another kind of criticism due to Mary Hesse and others is that, well, according to the orthodox view, we get these concepts in the theory by deriving them from postulates and then relating that derived concept to observation. But if you actually look at the way science works, that's not where we get theoretical concepts from. We instead get them by reasoning from analogy, from concepts that we do understand to new ones. We develop new ones via analogies. And so we can't just plop down some formal theory and then ask, is this true? Because there's nothing to plop down until you develop these concepts using analogies. And because you developed these concepts using analogies from things that you observed, they are also understandable in observational terms. To go very briefly through the rest, Quine in Two Dogmas of Empiricism argues that different parts of the theory can't be differentially related to the evidence. That is, according to the orthodox view, there's some parts of the theory that are directly related to observation, and there's some parts that are indirectly related. And Quine thinks and argues that that's not really something that you can maintain. There's no real way to keep that split firm, or at least firm enough to make this kind of instrumentalist move. There's a certain picture of explanation that goes along with the orthodox view of theories. It's sometimes called the layer cake picture of observation because it's based on this three-layer structure of the theory, the derived concepts, and the observed concepts. And it says to explain what goes on in the middle, you derive it deductively from what goes on at the top. To explain the observed stuff, you then derive that from this middle layer. And Feyerabend and Sellers, again, have pretty sustained criticism of this kind of picture. That's just not the way that scientific explanation seems to work. And then there's this sort of more linguistic or semantic argument from Sellers that if you look at the logic of theoretical terms, they work just like observables do, right? When you talk about when you're in the lab or in physics class and talking about the kinetic theory of gases, you say things like, well, this gas has this pressure because this molecule is bouncing against the wall with this velocity. And that means that you're saying there's a thing bouncing against the wall with a certain velocity. What is that thing? It's a molecule. You're saying that molecules exist because you've just said this molecule is doing something. And that's, what existence means, is that there are these things that have these properties. So these are all various criticisms targeting the idea that this orthodox picture of theories can be the right way of understanding both the internal structure of a theory and how that theory relates to evidence. Now, these days, at least in the parts of philosophy of science that I want to talk about today, most people find these kinds of criticisms compelling. I think broadly speaking, most people in philosophy of science are, in this literature anyway, are realists, at least of a sort. Let's just say that they're not instrumentalists of the sort of old-fashioned kind. And so because of this, they need to come up with a different picture of theories that isn't the orthodox theory, but hopefully, hang on to the features of the orthodox theory that were right or were convincing. The result of this in, say, 1965 or so, this is very rough, but the result of this is to say, okay, the split that the orthodox view of theories had between theory and observation, it's not so simple, right? It looked, according to the orthodox view, there's this really clean separation between the abstract theoretical stuff, the concrete observational stuff, and then certain individual connections between different points of each. That doesn't work. And that means that there's no real good reason to treat unobservables and observables differently. According to the orthodox view of theory, this is a difference in the kinds of things, right? Unobservable things are part of a theory. You can't really ask if they exist. You can just ask if they're useful organizational tools, observable things. You can ask if they exist or not. You can observe them or not. You can interact with them directly or not. If all of these criticisms about the theory observation split are right, then you can't maintain this distinction. What you should instead say is that whether something is observable is really a fact about us and about the sort of powers that humans have of observation. It's not a feature of the things themselves. And because of that, theories shouldn't, or when we think about theories, we shouldn't make this really sharp distinction between the observable and the unobservable, because we should just be talking about the world and the things instead of how these things are related to us. And so theoretical talk ends up being meaningful in just exactly the same way that observational talk is meaningful. So if a theory says that there are molecules, or if a theory says, quote, there are molecules, then it says there are molecules. According to the orthodox view of theories, that's not the way we should think. According to the orthodox view of theories, if a theory says, quote, there are molecules, what that means is there are certain propositions in the theory that can be inferred from each other. Here we can infer one using the existential elimination rule, and that will give us some sort of claim that through further derivation we might be able to connect to observation. But certainly it doesn't say that there are molecules in the sort of everyday sense. That's the old-fashioned picture. According to, if we want to go with the criticisms I mentioned, we have to say, no, when we say there are molecules, that's like saying there are laptops, there are radiators, there are glasses of water. Similarly, if the theory says that space or space-time is curved, then it says that space-time is not flat, because being curved means being not flat. And so what happens is that, if you like, the structure of the theory sort of extends all the way out directly to the world. And so we can still talk about the kind of formal structure of the theory, except now it's going to also include the things that are out there, right? I say this just because there are two ways that this could go, right? Given these criticisms, you could say, oh, well, I guess I was just wrong about what scientific theories are, and I guess there isn't any sense in which they're similar to mathematical theories, and there isn't any sense in which they have a formal structure. There's just, everyday talk, and there's nothing formal we can say. That's one way you could go, but it's not the way that most people in this literature have gone. There are a couple people that did go this way, but, I'm setting them aside for now. I think, broadly speaking, the reaction to these kinds of criticisms has been to say, oh, actually, that means that the formal structure of the theory is bigger than we thought it was. And it also includes things that say we can observe. And so now, if we want to talk about theories, that's going to have to include more than it used to. And so there's going to be more to talk about. And there's going to be more to talk about when we want to answer these questions about theories that are posed in philosophy of science. Okay, so that's kind of like the really, really broad setup of philosophy of science. Here's a particular issue in philosophy of science, the issue of realism. This issue motivates the fact that we need to care about theories, or at least it motivates a specific notion of theory that philosophers of science tend to care about. And so this is the context in which one might think that there's something worth saying, formally speaking, about a scientific theory. We used to think that there was relatively limited, not that limited, but relatively limited formal structure to a theory. Now we think this formal structure extends, as it were, all the way out to the objects themselves. So if we think we have this really big formal system that extends all the way out to the objects themselves, we ought to have a way of talking about what kind of formal system it is that we're talking about, right? And here's where the sort of connection to the mathematics is going to come in, and the formal philosophy of science itself is sort of enters, right? Because if we think that the theory is a formal system, we can ask, what kind of formal system is it? And by that we mean, what is an abstract characterization of theories in general? So I mentioned way back on that first contentful slide that you can, of course, ask questions about individual theories and about how an individual theory is related to evidence. But you could also ask these questions in general about what's the relationship between theories and evidence. And if you want to ask that kind of question, then you need to be able to say, in general, what a theory is like. And so far, I've only said, oh, it's kind of like a formal system, kind of like, mathematical theories, right? The theory of the kinetic theory of gases is analogous to the theory of groups, or the theory of topological spaces, or something like this. So what we want is a theory of theories, if you like. And in the orthodox view, given the time of writing, 1920s or so, you go look over the mathematicians, and what are they doing? Well, they're developing proof theory. So proof theory is a theory about mathematical reasoning. Why don't we just try to take that mathematical theory and apply it to scientific reasoning, to natural scientific reasoning? That's really what was, behind the general characterization that I was giving you of the orthodox view. There were different specific pictures of how exactly the proof theory entered, but by and large, everybody said, look, proof theory, that's where it's at. That's what I mean by a formal system. I'm going to understand a theory as being a collection of axioms in the sense of proof theory, and I'm going to understand the consequences of the theory as being, the consequences of the theory in the sense of proof theory. Critics of this orthodox view tended to prefer model theory. Now, this is in part because of just temporally model theory developed later. But this also has to do with shifting philosophical attitudes towards proof theory and model theory that I don't want to right now anyway get too deep into. I just sort of want to flag that there was this change. So let's say something a little bit more concrete about these different proof theoretic and model theoretic approaches to modeling scientific theories. So in the proof theoretic model, which is meant to coincide basically exactly with this orthodox view of theories I mentioned, a theory is a set of sentences in some language L, right? So this is doing some mathematical logic. Mathematical logic studies consequence relations within languages, formal languages. A formal language consists of things like terms, predicates, functions. Some of these terms and predicates are observable, or if we're careful, because they're part of the theory, it's the stuff in the middle layer that gets directly related to or coordinated with the observable stuff. So, systems of molecules. These form a subset, call it O, of L, that is called the observable language. So there's a split in the whole language. We've got a bunch of terms and predicates. Some of the terms and predicates are observable. Everything else is theoretical. Call this T. This is just the complement of O and L. This split is supposed to track the split between the formal theoretical stuff at the top and the concrete empirical stuff at the bottom. The way that this gets used in the formal model of the theory is to say that sentences that are formulated purely in the language O have meaning given by observation. These are things that, as far as we're concerned, we understand sort of without having to do any theory. This is the stuff that's just directly part of what we can observe. Everything else, sentences that involve theoretical language, T, they get their meaning from implicit definition. So what is a line? Well, it's anything that satisfies the axioms that I gave you on the previous slide. What's a line in hyperbolic geometry? It's those. What's an identity in a group? It's anything that satisfies the postulates that I gave that identity has to satisfy in a group. What's a molecule? It's anything that satisfies the features that are postulated in the kinetic theory of gases. And there's really nothing more to say according to this picture. So we've got a language, we've got the split in the language between theory and observation, and then we can relate sets of sentences in this theory using a proof theoretic consequence relation, right? This is just modeling deduction. And so these are the basic tools, and then we want to understand the sort of the dynamics and the structure of scientific theories just in terms of proof theoretic consequence, derivation. So I mentioned before that on this picture, a theory explains observations by deducing them. This deduction is what's being tracked by a consequence relation. The theory predicts things by deducing them. That's what's being captured by the consequence relation. Now, predictions, explanations, etc. There's going to be more that we have to say about what exactly goes on there, what exactly the structure of the projection has to be, what other kinds of assumptions are involved. But at least as a first pass, in the proof theoretic model, the basic ingredients are a formal language and a consequence relation. And those are the things that we want to understand the theory, scientific theories in terms of. Okay, so it's been a while and I haven't said any sort of theorems, right? And so whenever you're introduced to a formalism, the first thing you should ask is, well, give me a theorem that I can use this for. So one theorem that was used in this formal model of scientific theories is Craig's theorem, which, if you are not familiar with it, just essentially says any set of formulas that we could care about, any scientific theory, let's say, is primitively recursively axiomatizable. So any recursively enumerable set of formulas is primitively recursively axiomatizable. If you don't know what the stuff in parentheses means, don't worry about it, because in this debate, people didn't worry about it either. The thing what they worried about is the following corollary of this theorem. For any theory T in a language L, the set TO of consequences of T in the language O is axiomatizable. What does this mean? Well, let's think about what the different ingredients here mean. So L is the language that contains all the theoretical and the observational stuff. A theory T in this language is going to be a set of claims in that language. And so here we're thinking of the full scientific theory. It includes stuff about molecules and systems of molecules, which is to say boxes of gas. In this theory, and all of the consequences of it, right? So here we're thinking of a theory not just as the postulates or the axioms, but also all of their deductive consequences. Some of these consequences, call that set of consequences TO, that's going to be the set of consequences of T that only use, that can be formulated purely in the language of O. That is, this is the purely observational part. This is the kind of stuff that we think has meaning independently. And we think everything else is the stuff that's theoretical and therefore essentially meaningless, or at least not meaningful in the sort of full-blooded sense that the observational stuff is. And so TO is the stuff that is, actually about the world. These are the consequences of the theory that we think are the, the empirical content, if you like. This is the stuff that the theory actually says about the world. TO is going to be a subset of T. It's going to exclude all the theoretical stuff, all the claims about molecules and things like this. What this corollary says is that if your set of theories is recursively enumerable, which people just assumed due to the way that scientific theories are, this would always happen or usually happen, then you can axiomatize the set TO directly using just the language of O. And the interpretation that people gave of this theorem, so for example, Hempel in 1958 gave of this theorem, is that this is a precise sense in which we can say that the theoretical stuff in the theory, that is in the part of the language L that is not purely observational, that stuff is dispensable but convenient. Why dispensable? Because in principle, according to Craig's theorem, we could rewrite our theory to not make any mention of anything except what's in O. And so in principle, we could just get rid of all the theoretical stuff and have a theory with exactly the same empirical consequences. And so it would be just as good when it comes to the meaningful stuff. On the other hand, it is convenient to have the theoretical stuff because just saying that the theory is primitively recursively axiomatizable is actually not saying much, because in general, if you follow the details of Craig's theorem, one finds that there will be infinitely many axioms, right? And it's kind of hard to write down a theory with infinitely many axioms because you run out of paper. And so what we should do in practice is to use theoretical stuff because it's useful, but don't take it too seriously, because you could, if you like, cash out the theoretical stuff in the empirical consequences that it has. You could, according, and this theorem is meant to be kind of a proof of concept, right? It underwrites this claim that in principle you could get rid of all the theoretical stuff and be left with, the real stuff, the empirical regularities that can be phrased only in the language of this observation. Now, there were various objections that targeted specifically this kind of move. So here's one from Wilfrid Sellers in his paper, The Language of Theories, from 1961. he points out that what Craig's theorem shows is that you can derive certain sentences that are formulated only in the observation language using the theoretical stuff. And people interpreted this as saying, oh, well, that means that we can recover all of the like phenomenological laws, right? So Kepler's laws is an example they would use. So Kepler's laws say things like, the planets orbit the sun in ellipses with the sun at one focus. And they sweep out equal area and equal time. And the third one is always complicated in a way that I can never remember off the top of my head, but involves a certain power law between the median distance and the period. And when you look at these Keplerian laws, you think, well, ellipses, that's something I can basically see. I have to use a telescope, but I can essentially observe the orbits of the planets just fine. And Newton's laws derive Kepler's laws. And so Newton's laws are better because they're more, let's say, expansive or general. But if I needed to, I could get by using just Kepler's laws because those are ones that are purely observational. The thing that Sellers points out is actually Newton's theory does not derive Kepler's laws. What Newton's theory shows is that in appropriate limits, one recovers something that is approximately like Keplerian laws. What is that appropriate limit? Well, it's the limit where there's the mass of the sun is significantly larger than the masses of all the planets, and therefore it's not itself moving too much. And the other planets are not affecting each other too much because they're far enough away. And so there's certain assumptions about the other forces not being too strong. But now I'm talking about masses and forces and things like this. And that means that I'm talking in the theoretical language. And I can't formulate the actual regularity that you get from Newton's laws without using theoretical language. And so this is part of, I mentioned before, the Salarzian critique of this orthodox view of theories. There isn't a middle level that's purely observational and derivable from the theory. There's this middle level where using the theory, you can say things about observation, but the things that you're saying can only be said if you use the terms of the theory. And because of this, we shouldn't interpret Craig's theorem the way that, say, Hempel did. At least, this is what Sellers argues, and this is what people find very convincing. Worse than this, there's an argument from Doss and Frossen that you can't actually sort terms according to whether they are observable or not. We're working with this idea that you can split the theory into observational and theoretical by looking at the word that's being used, right? You can say things like molecules are unobservable, boxes of gas are observable. But that's not actually true, or at least it's not obviously true. So what's a monocrystal? It's a really, really big molecule such that you can see it, right? It's big enough to see. So in fact, you can see molecules, or at least that's a way you can use the term molecule, right? Here, one needs to have something of a fight about what exactly molecule ends up meaning, but that's a perfectly reasonable thing to mean by molecule. Another example, cosmic visual ray phenomena. Astronauts often see these certain kinds of bright flashes. The going theory is that what's going on there is that a cosmic ray is passing through their eyeball and then, stimulating their retina, and then they're seeing a cosmic ray. What's a cosmic ray? Well, sometimes anyway, it's an electron. So it turns out you can actually see electrons. Usually you can't, of course. Usually, in most contexts, electrons are the kinds of things that one cannot see, but in other contexts they are. The conclusion that Van Frossen draws from this, which other people, for various reasons, either because they agree with Van Frossen or not, agree with, is that, like I said before, whether something is observable or unobservable isn't really a feature of that thing. It's a feature of that thing and us and the context. And so trying to sort observable and unobservable linguistically is going to be hopeless, right? You're not going to be able to say there's certain kinds of words that correspond to observable things, certain kinds of words that correspond to unobservable things. Rather, the observation, observable, unobservable split does not match up with the theory, or does not match up with a linguistic division between kinds of terms. So these are only a few of the kinds of complaints about the theory-observation split that I mentioned way back before, but these are the ones that are most directly about the kind of formal aspects of the orthodox view of theories. Here, this is a complaint about this idea that the way we should understand scientific theory is by analogy with mathematical theory in the sense of proof theory. Okay, so the orthodox view, as I said, involves a certain proof theoretic model of what a scientific theory is. And I mentioned now there are a couple of criticisms of it. There's the broad criticisms of the orthodox view of theories overall. And there are also more specific criticisms of the proof theoretic model of theories that the orthodox view of theories assumes. For reasons including the criticisms that I have mentioned now, philosophers of science, formal philosophers of science, have tended to move away from proof theoretic treatments of theories towards model theoretic treatments of theories. On a model theoretic model of scientific theories, a theory is a class of set theoretic structures. These structures are the models of the theory. One should be thinking here of model theory in the mathematical sense. There's, given a certain signature, there are various structures in that signature. Some of these structures in that signature are models of the theory. The idea of the model theoretic approach to theories, or the semantic approach as it's sometimes called, is to say, well, model theory gives us the distinctions and notions and concepts that are actually relevant to understanding the structure of scientific theories. Proof theory sort of carves things up the wrong way, right? It said, well, I can distinguish between that kind of term and that kind of term, but just the joints in our language do not directly map onto the joints in the world, and so we shouldn't be talking about features of our language. We should be talking about features of the models, which, the thought goes, are going to carve things up differently, and so they're going to be able to let us distinguish between, say, the observable and unobservable in a better way, a way that keeps track of the fact that it's a fact about us rather than the objects, things like this. Okay, so in this case, how do we relate? Okay, so that's the general picture. We're going to use concepts from model theory instead of proof theory. What does this amount to in practice? Well, it amounts to using essentially maps between models instead of talking about consequences between sets of sentences. So the idea is these models are going to be related to each other by different structure-preserving maps, model theoretic homomorphisms, and they'll also be related to the world via these structure-preserving maps. And so there's going to be some reduct of this model that captures the empirical content, and if that empirical content is isomorphic, or appropriately, there's a fight here about, do you want isomorphism, do you want injection, in which direction, but if there's a structure-preserving map of the appropriate kind between the world and the model that it captures the empirical content, then your theory matches with the world the right way. And that's different than saying if the purely observational sentences are true in the world. Or at least it's a different way of thinking about it that leads you to say different things, at least at first pass. So if we say, let's use model theory instead of proof theory, then this presents us with a new kind of research program. Take the typical questions that the orthodox view of theories addressed and replace their proof theoretic strategy for answering them with a model theoretic perspective or strategy. And I've already suggested at least one way that, one kind of place where these will come apart, right, is in picking out the observable content of a theory, right? So the observable part of the theory is going to be something that's relative to us, but it's going to be something that it is still, there's a fact of the matter about what humans can perceive. And it just happens that what we can perceive isn't tracked by the words that we have for things. Sometimes we can see things, there's certain, for any let's take the cosmic ray example. Some cosmic rays we can see, some of them we can't. Saying that something is a cosmic ray does not imply anything about whether it is observable. The idea of the model theoretic model or the semantic model is, well, if we use model theory, then we can more accurately capture what is observable in a theory, because we're not tied to any particular words for things. We can instead capture the events themselves, the observation events themselves, or the observable features themselves. So that's one place where this new research program is going to diverge from the old one. Another place that the two approaches will diverge is in the case of laws. So this is just an extended example of one place where the proof theoretic and model theoretic approaches will give you different answers to questions. So according to the orthodox view, a law is a statement of the form if X then Y. Now, X and Y are going to have to be increasingly complicated. And of course, if you want to look at real examples, they're going to have to be really complicated. But the idea is, look, what do we have? We have sentences and consequence relations. What's a law? I mean, I guess it's got to be a sentence, because it's not going to be a consequence relation. I shouldn't have said that. Anyway, the basic tools in the proof theoretic approach are sentences. What kind of sentence could a law sentence be? Well, at the very least, it seems like it's a conditional. For example, if two bodies have mass little m and big M, and they're separated by a distance r, then each exerts a gravitational force proportional to mm over r squared on the other. So this is the statement of Newton's law of gravitation, according to the orthodox view of theories. This sentence is a law. That means, among other things, that it's a conditional sentence. What do we do with laws? Well, we use them in deductions. In particular, we use them in explanations. So an explanation, that's a particular kind of proof. According to the orthodox view, an explanation is a certain kind of proof. It's a proof that includes a law as a premise, it includes certain conditions as another premise, and then the conclusion is going to be the thing that is being explained. This presents us with particular puzzles. Which statements are laws? So this says that a law has to be a conditional, but usually one's going to have to say a bit more, right? Not every conditional is a law. How do you distinguish between the conditionals that are laws and the conditionals that are not? Another puzzle, how do you justify law statements, right? How could you, using observation, demonstrate that if X, then Y? Well, I mean, it seems like the only thing you could do is to go look at a whole bunch of X's and see if they're all Y's. But logically speaking, you could just as well go look at a bunch of not Y's and show that they're not X. And that's going to be just as much evidence. And this is called the Raven paradox. It seems to pose a problem for the proof theoretic approach to scientific theories. More devastatingly, I suppose, is, really, according to the official view of the orthodox view, the law statements are not just conditionals, they are rather universally quantified conditionals. Really, so it says something like, for all bodies, right, for all pairs of bodies, if they have these masses in separation, then they act a certain way. But in order to verify a universally quantified sentence, it seems like you have to check every case, and there are too many cases, and so you can't empirically verify laws, it seems. And so this is what is sometimes called the problem of induction, or at least a first pass at it, right? And so then the question is, how can we understand the relationship between law statements and observation such that it's possible to, using observation, investigate law statements? So, right, okay, so this is supposed to be an example of the difference between the proof theoretic and model theoretic approach. In the case of laws, the proof theoretic approach says, well, a law is a certain kind of conditional, and then this leads us off into certain philosophical projects in trying to understand which conditionals exactly are laws, how do these laws relate to other things. The model theoretic approach says, well, no, look, a law is a statement about what has to happen, not just, every time that X happened, Y happened. No, every time that X happens, Y has to happen. And so if we want to talk about laws, then we need to talk not just about conditionals, but about some kind of logic of must statements. Now, it happens that in 1970 or so, logic of must statements, or modal logic, was devised, and the semantics for this logic was based on a notion of possible worlds, right? So the basic idea is that to say something has to happen is saying that it happens in every possible world. So the model theoretic view says, okay, I want to be able to talk about what must happen. In order to do that, I need to talk about possible worlds. Where could I get possible worlds from? Well, according to me, a scientific theory is a big collection of models. Why don't I just say that that collection of models is the collection of possible worlds? This is a proposal that has found wide acceptance, or at least it's a plausible first step for many philosophers of science and philosophers of physics in particular. And so, as you can see, this kind of treatment of a law, it's something that bottoms out in a collection of models, is quite different from the idea that a law is a certain kind of conditional statement. Obviously, you can do some work to try to connect the two of them up, but the connection is going to be very complicated. And so if you want to say in a sort of single line, what's a law? Here's the fight. Proof theoretic people say it's a conditional. Model theoretic people say it's a certain collection of models. So this was all meant to be sort of stage setting for how could category theory ever have anything to do with philosophy of science? Well, here's, at least broadly speaking, how one can start to see formal philosophy of science as a project. A lot of philosophy of science today is structured around this idea of a theory. When philosophers of science talk about theories, they usually have something like a corrected orthodox view in mind. Scientific theories are just like mathematical theories, except that we use them differently. And also there's this stuff about observation and about explanation and stuff. We have to make these corrections to the old-fashioned orthodox view to get something that's more plausible. The reaction to these criticisms of the orthodox view led to this expanded conception of theory, where now the theory that we're talking about in formal philosophy of science is not just the postulates and the definitions and their relations, but also stuff that includes the observable. And so now if we want to talk about, this gives us more to talk about when we talk about theories. And the thread that I wanted to particularly pick up in the criticism of the orthodox view of theories is a certain fight over what the right formal model is of a scientific theory. Should we use proof theory or model theory, right, is basically the kind of question. And there's historically, rich or complicated effects on which of the two options people went with at the time. But essentially nowadays, people in formal philosophy of science usually think that the model theoretic approach is more plausible and allows you to do more things and gets more things right and things like this. And so that's the one that we ought to use. And so this is one way that a formal theory of theories can come to bear on philosophy of science questions. So if it's all right with the organizers, I think I might take a break for just 5 minutes or so, and we can stand up and stretch our legs and things like this. Is that okay, Marcelo? All right. Yep. Sorry. Thanks though for the, and maybe I'll pick up at, yeah, great. 5 minutes. Maybe I'll start again. That sound all right? That works for me. Okay. Yep. Yes, hi.
Scientists will be agree with that because of three very important classical points. One is the idea of the explanation. I don't think we can just simply equate explanation with deduction, because if you can do that, so every mathematical proof it would be an explanation. I mean, mathematicians are not happy with everything. Like people are not really happy with the recent proof of this Fermat-Lat theorem, because it's too much complicated, and people are looking for better, more clarifiable explanation. From one point. Second point is that the aspect of previsibility, or like a theory can foresee or predict something. I don't know how you are covering this kind of topic. And the third, most important perhaps point, is the aspect of falsification or falsificationism. Like, like Popper puts that theory that every theory has to be falsifiable. And the theories you are putting in front of us, I don't see how can they be falsifiable. So from this point of view, I don't think that every scientist or everyone will be agreeing with this like a logical kind of model of theories. What can you say about that?
Yeah, great. Thank you. So, the video froze in the middle, and so I didn't hear everything that you said, but I did hear the first and the third. Was the second one about possibilities, did you say? Prediction?
Yeah, prediction.
Yeah, good. Okay.
review, predictability, like a theorist can predict the future.
Yeah, yeah, good. Right. Yeah. So yeah, I mean, I think these are, yeah, there's details and there's details. So good. I mean, I think the one thing that I didn't make clear enough is that, yes, as you said, explanation can't equal deduction because there are plenty of deductions that are non-explanatory, and you might think there are also explanations that are not deductions. So statistical explanation is a classic case where it seems as though one cannot deduce that some effect will happen. The best one can do is deduce that there's some chance that will happen, or it will happen with a particular kind of rate. And then one has to ask, how exactly does the predicted rate, how exactly does one match this up with the empirical? So on the explanation deduction issue, yes, I focused on a certain structural problem with the orthodox views understanding of explanation, namely their theory of explanation presupposes a certain kind of relation between theory and observation that it seems like is not tenable. However, as you point out, and I agree, there's other bigger problems with this, which is like explanation or deduction, it seems, can't be enough to make something an explanation, so something else has to go in. And probably there are going to be cases where there are explanations that just aren't deductions, right? And so I listed these puzzles before about what laws are. These were traditionally understood as puzzles for accounts of explanation, because the idea was, well, not every deduction is an explanation. Why not? Well, because some deductions don't involve mention of laws. So something can only be an explanation if it mentions laws. And then it still isn't always going to be an explanation because some deductions involving laws don't count as explanations. And so we need to have further kinds of constraints. And we also need constraints on what a law could be, because it looks like there are often generalizations that are not laws. Moreover, this assumes that there can't be explanation in mathematics because, you know, there aren't, it does not seem that there are laws in the same way. So I think there's a lot of criticisms here that are all right, and these are all problems with the orthodox view. And I think that there's two kinds of attitudes that one can have about this. One is to say, well, the problem with the orthodox view is that it thinks that it can give a formal treatment of explanation, and that's wrong. That's a kind of criticism that would say we shouldn't even be doing the formal thing at all, and so forget about it. There's a second kind of criticism, and that's not the thread that I have been following, though there are certainly people that have this kind of attitude. The thread that I was wanting to follow was rather people who said, look, deduction is just the wrong kind of thing to try to match up with explanation. What we ought to do instead is to understand the structure of explanation as being something just totally different from deduction, or more complicated than, or related to in some way. So let me be concrete about this, for example. So according to pragmatic theories of explanation, what makes an explanation is not that it's a deduction of a certain kind, but rather it provides evidence in, or it provides just it provides some true claim in a certain kind of context. It's a certain kind of context that has to do with inquiry, where there's a certain question that's salient and up for debate. And when you ask, you know, why did such and such happen, what you're doing is you're asking for a certain kind of information. And so in this, on this pragmatic theory, right, what makes something an explanation is that it's being asked for. And so it's playing a certain practical role in the conversation that's being had. And so here, deduction is just the wrong thing to be talking about. We should just be talking about what is the formal structure of the inquiry context such that providing this information will count as an explanation. So, right, what I wanted to convey was explanation. And this is supposed to be in favor of the model theoretic approach against the proof theoretic approach. There's an interesting thing, or like one more interesting thing though about the explanation deduction point that you raised is, you know, this is something I'm also interested in. It seems like in mathematics there are explanations of things, and the notion, the models of explanation that one gets in philosophy of science, I think, are not appropriate to mathematical explanation, or at least it seems it's very hard to make them fit And if you want to do so, you need to do some pretty weird things, right? So most of the time in the literature that I'm familiar with, what people will do is say, look, there's mathematical explanation. This theory of explanation doesn't capture it, and therefore it's a bad theory of explanation. And there are two kinds of reactions one sees. One reaction is a kind of limiting one where they say, well, I wasn't only trying to understand natural scientific explanation and not mathematical, like, so I shouldn't apply to mathematics. And so that's kind of a limiting kind of response. Another kind of response is to say, no, if you, wiggle around the details enough, then you can actually apply this to mathematics as well. So I have a colleague, Alexander Reutlinger, who with co-authors has tried to show that these counterfactual modal approaches to explanation do work in mathematics, despite the fact that one wants to say that mathematical claims are all necessary. But he, says that the point of that is to be kind of a proof of concept to show that, strictly speaking, one could analyze mathematical explanation in that way. And he's not convinced, at least last time I talked to him, he's not convinced that that's the right way to go. And I personally don't think it's the right way to go either, though I don't have any very clever ideas. On the point about predictability, this is, is the point roughly similar that, again, prediction can't be deduction either, because prediction, if, the orthodox view says prediction and explanation are the same thing. It's just that one has a conclusion about the past and one has a conclusion about the future. That's the traditional view. That doesn't seem right. It doesn't seem right for various reasons, but that's not a criticism that I mentioned. That wasn't because I think it's wrong. I do think that that's prediction and explanation are different things. That's just not something that had come up. But this is another problem, I think, with the orthodox view that I think runs into it's a similar kind of conversation that one has with explanation. As for the falsification, you're right, I didn't mention it because I very, very briefly skipped by what the model theoretic attitude is when it comes to the relation between theory and observation, right? So the story about falsification in the orthodox view is really quite clear. You've got your theory, you can derive consequences from your theory. Some of those consequences will be observable. Go check. Are those consequences, the observable consequences, true? If they're not, throw out the theory. If they are, then your theory passes the test, right? So this is the sort of orthodox Popperian notion of falsifiability. Start with whatever theory you like, derive some consequences, check them. And we know what it means for a consequence to be true because the consequences that we've derived are coordinated with observation language, and we understand observation language, so there's no question about how to test it. I mean, there's practical questions about what exact equipment we ought to use and things like this, but there's no sort of philosophical question about what falsification would involve. The question is a lot more complicated in the model theoretic case, but in a way that I think people didn't initially realize. So the kind of first pass model theoretic approach that people tended to take was, well, there's some part of our model, right? I mean, there's sort of a reduct in the language to the language of, to the structure that is in the observation language, roughly speaking. And either that's isomorphic with the world or it's not. And if it is isomorphic with the world, then the world does fit in the theory. If it's not isomorphic with the world, then it doesn't fit the theory. And here, on the one hand, it's kind of, what do you mean isomorphic with the world? The world isn't a mathematical structure, right? So how could it be isomorphic with the mathematical structure? So that's one kind of worry. But the reason that I think, at least initially, the model theoretic approach didn't worry so much about it is because they thought, well, what we've done now is we've extended the theory all the way out to the world, and so now everything we understand, right? The orthodox view thought we only understood the observation language, and so in order to falsify something, we had to formulate it in the observation language. But if we think, extend it all the way, bring the theory and observation together, put that all in a model, then we understand the whole model. And so we just need to check whether that model is isomorphic to the world, and there's no big worries about that. Eventually, that does, of course, become problematic. And one of the two examples that I'll give about uses of category theory in formal philosophy of science is about confirmation issues or falsification issues, and the ways that category theory has been used to try to intervene on that kind of debate. But so, I mean, does that at least as a first pass respond to what you were asking? Yeah. No, I'm 100% with you, and like to be a little autobiographical about it. I mean, that's my biggest worry about all of this is like it is a huge approximation or idealization or simplification. So my own training was in particle physics initially, and so I think of everything is a simple harmonic oscillator. And so sometimes there are things that are 2 or 3 or infinitely many simple harmonic oscillators, but basically everything can be understood that way. And of course, that's a kind of ridiculous oversimplification. And the thing, I feel like there's a kind of, but when I do feel that formal philosophy of science approaches can be plausible, it's very often in a way that I think physical models can often be plausible, where you can get maybe some aspects relatively correct, but there's going to be like way more detail than you're possibly going to be able to handle when you're talking at the level that I've been talking at. And so one thing that I would like to be able to say more clearly is the sense in which these proof theoretic, model theoretic, modal logic, etc., are like kind of general orientations about how to approach certain kinds of problems. And in part because I haven't been talking very concretely about specific problems, I feel like I've remained at a pretty abstract level. And so, yeah, I mean, I agree that this is talking at this sort of broad level can at most be sort of a story about how could you ever think that, these sorts of math, one could do something with formal tools in philosophy of science. It's not yet to show that anything productive has or could in fact be done. But so, yeah, let me then give 2 examples that are at least meant to be more concrete applications here, if that's all right. Okay, so good. Okay, onto this. So one of the reasons that I want to talk about category theory here is that I've talked to Marcelo before about his interests in category theory and philosophy of science, and so I thought that because that's a topic I'm interested in, it's a topic that comes up in my work, it would be, a nice topic to talk about. So one thing I'll say is that category theory, if you're familiar with it, it has a great many aspects. It's kind of famous for having a whole bunch of perspectives on it and different ways that one can approach it. I want to talk about one aspect of it, which is a framework for working with classes of structures. What I really have in mind here is the way that category theory gets used in algebraic geometry and algebraic topology. I'm not going to talk about those examples in particular because I'm going to assume that people are not, deeply familiar with category theory anyway. But at this general level, this idea that category theory can be a framework for working with classes of structures, that's what formal philosophy of science is about, at least the way I've set it up. And so, look, there's at least a plausible kind of connection here. Now the question is, how do the details actually go, and can you actually do anything with this? And so I'm going to give 2 examples where people have at least tried to do so. So to motivate talking a bit about some of the categorical terminology, let's consider an example. For any set X, we have a power set, that is a set of subsets of x called as px. This is something like a function that takes a set and gives a set out. It can't really be a function in the strict sense because there's too many sets, so it can't, the domain here, the class of all sets, and that can't be a set by Russell's paradox reasons, or Brawley 40, or you choose your favorite one. But it's something like a function. And one way that it's something like, and not really a function, are these domain and codomain problems. But another way that it's something like a function, but not quite, is that it includes more structure. So not only does, for any set, not only is it the case that for every set we have a power set, but also for any function f from x to y, any set function, we have a function f star from py to px that takes any subset v of y to the set of x such that its image lies in v. So this is a pre-image function that maps between the power sets. This is an example of what in category theory is called a functor. The term functor comes from philosophy of science. Actually, it was taken as something, not a joke exactly, but kind of a joke. A lot of the terminology in category theory is motivated by philosophical terminology because the person who introduced much of the basic terminology, I guess, thought it was funny. But okay, so what we've got here is something like a map. When I say something like a map, what I really mean here now is it's a functor. That is to say, it acts both on sets and on arrows between sets and gives you some output, in this case a set, and maps between these outputs. Here's another example. For any set x, we have a set of maps from x to the set of two elements, called it 2 to the x. This is the set of functions from x to a two-element set. I'll just use bottom and top as the two elements. Moreover, for any set function from x to y, we have a set function from 2 to the y to 2 to the x that acts in the following way by post-composition, pre-composition, I guess. This is another functor. It's a functor that takes a set, gives out a set, takes a map between sets, gives out a map between the outputs. Now, those of you who are familiar with this sort of thing will recognize that these are really the same thing, right? I mean, the power set, I mean, there's a sense in which they're not the same thing because the power set is the set of subsets and 2 to the x is a certain set of functions. And so if you look at these theoretically, 2 to the x is going to contain sets of pairs, and p to the x is just going to contain sets of elements of x. But there's a natural way to identify them by identifying a subset with its characteristic function. So to be more precise about it, for every x, there's two bijections. There's a bijection alpha x from 2 to the x to px that sends any function to the set of elements of x that are sent to true by that function. And for any x, there's going to be a map beta px to 2 to the x that's going to send any subset of x to the function that sends an element of x to true if x belongs to that subset and false otherwise. So this is an example of a kind of natural identification that mathematicians, I think, make without really thinking about it, because it's not hard to make without really thinking about it. And once you're sort of comfortable enough with 2 to the x and px, it's one really rarely even makes a notational distinction between them. Nevertheless, there is, if you want to be super careful about it, a precise sense in which they are not equal, because one's a set of sets of x and the other one's a set of pairs. But the point, or a point, of category theory is to provide machinery for working with natural identifications of this kind. Because even though in this case it's so simple that you don't want to think about it because that's too much effort, there are other cases where one seems required to think about it and you don't want to think about it. And so the hope is that you can have a kind of nice, if you like, language or framework for working with these kinds of natural identifications without too much stress. And so this is the one of many perspectives. This is the one that I want to take on what category theory is up to. It's a way for handling these kinds of natural identifications. So how do we need to, what exactly is involved in making sense of this kind of natural identification? Well, let me just introduce some notation here without getting too much into the details. A category C is a collection of objects I'll also call C. And for any two objects in the category, there's a set of functions or maps, the arrows from one to the other, that I'll use function notation for, like this, right? So here, one sort of mother of all categories is the category of sets. So you can think here, the category of sets has the collection of sets as a set of objects. And for any sets x and y, there's a collection of functions from x to y. And these functions or maps or arrows are required to satisfy the usual sort of function identities. You can compose them. There's an identity. Composition is associative, and the identity acts as the identity. And so the point of a category is to serve as a domain and codomain of a functor, where the functor, recall, is this kind of souped up function between classes of structures. So here's some examples. Sets and set functions, that forms a category. Groups and group homomorphisms, that's another category. Topological spaces with continuous functions is a category. Smooth manifolds and smooth functions. Partially ordered sets and order preserving maps. And the one that will be most relevant for us, the collection of models of a logical theory and homomorphisms between them forms a category. In fact, models, homological theory are a nice example of the fact that you can have lots of different categories with the same collection of objects. You could also talk about the elementary embeddings here. But I'm just going to talk about the model homomorphism case because that's what people in this literature tend to talk about. So I said a point of a category is to be a domain or codomain for a functor, where a functor is this kind of souped up function. More precisely, a functor from C to D takes every object of C to an object of D, and every arrow of C to an arrow in D, in such a way that identities and composition are respected. And so, yeah. So examples here, the power set functors that I talked about before, that take any set to a set of subsets, or any set to the set of functions from that to the two-element set. These are two different functors. There's a functor from the category of groups to the category of sets that sets a group to its underlying set. There's a functor from topological spaces to the category of groups that sends a space to its fundamental group. That's the set of pointed maps, momotopy class of the pointed maps from the n sphere to x that I mentioned on the previous slide. There's a map from a functor from sets to groups that sends a set x to the free group on x. Okay, and so these are the kinds of things that we're going to be able to, or we're going to want to be able to naturally identify, right? These sort of power set functors being the first example. And then the two examples of category theory and formal philosophy of science that I'll talk about are also about using this sort of natural identification idea. In order to naturally identify two functors, we talk about a natural transformation. This is a natural transformation from a functor F to a functor G is a collection of arrows, one for every object of C, in such a way that the composition structure is, in such a way that the action of the functors on arrows and on objects is compatible with the two. So I'm flashing this up here just because I sort of feel obligated if I'm going to talk about a mathematical definition in this context, I ought to actually write down the definition somewhere. We don't actually need any of the details here, but this is what it looks like. And that's the end of the definitions that I'll be introducing. What we need to be able to talk about are functors and natural identifications. And at least at the level I'll be talking about, I'm just going to keep saying natural identification, and I'm going to stop doing the quotes thing because my fingers are tired. So here are some examples of natural identifications. There's the natural isomorphism between the power set functor and the exponentiation to functor that I talked about before. The other favorite example people love is if you have a vector space V, there's a natural transformation that whose component for V maps from V to the double dual of V that sends any vector V to the element of the double dual that evaluates a function V. Maybe some more kinds of set theoretic one. There's a natural isomorphism between the product of X with the disjoint union of X, Y, and Z, and the disjoint union of the product of X with Y and the product of X with Z. This last line, you can write down similar examples using Cartesian products and disjoint unions that an exponentiation that looks a lot like kind of basic arithmetic, but now you're talking about sets with Cartesian product and disjoint union instead of numbers with multiplication and addition. So these are the kinds of natural identifications that one, I think, regularly uses in mathematics and are meant to be the kind of thing that the bit of category theory I'm talking about sort of takes care of without stress. Like the point of it is you don't want to think about these being different, because even though strictly speaking, there's a sense in which they're different, you don't want to have that difference in mind. Right, so there's the summary for what I'm going to talk about today. The basic notions here are category, functor, and natural transformation. The way that computations in category theory in this framework that I've mentioned work out usually is you combine a whole bunch of natural transformations, especially natural isomorphisms. And the reason to do this is that these help you handle a lot of data at once and focus on sort of what really matters, right? So one reason that category theory ends up getting being so useful in, say, algebraic topology is because there one needs to think about families of sets indexed by natural numbers and various maps between them, and being able to have a framework in which you can think of this family as a single thing is very convenient for doing actual calculations. And in fact, the category theory originally was introduced as a framework for doing certain computations in algebraic topology of homotopy groups of solenoids, if that means something to you. And so the way that you would do this computation is to show that the abstract characterization of what the homotopy group of this space would be is naturally isomorphic to something that's a lot more accessible to calculation. Okay, so that's then a very, very brief statement of one aspect of one thing that category theory can do for you. What does this have to do with qualitative science? Well, observation, category theory provides a third set of tools for talking about mathematical theories, right? So I've said before, there's this proof theoretic approach to talking about mathematical theories. There's a model theoretic approach to talking about model theory, scientific theories. Well, category theory seems to have the similar kind of generality that when we want to talk about theories at this really general level, we should be able to use category theory just as well. And this presents a general idea, do the same thing that we do with proof of model theory, but with category theory, see what happens. And this has been essentially the way that people have pursued this in the literature. In particular, what they tended to do is to augment the model theoretic approach with categorical concepts. So they say, we understand the sort of model theoretic approach to scientific theories, and the category of models, or the class of models of this theory set, it naturally looks like a category. And so why don't we just try to treat it as a category and see what happens? And here are two examples of where people have found some kind of payoff in doing this. The first comes from confirmation, right? So confirmation, I mean this in the very general sense of just, we have this theory, we want to know how can we come up with evidence for it? Or evidence against it, right? So confirmation, more in the narrow sense, means evidence for it. Falsification in the narrow sense means evidence against it. I want to talk just here about, there's got to be evidence for and against different theories. How do we talk about the relation of the theory to the empirical evidence? There's a common intuition that if two theories are empirically equivalent, then there has to be equal reason to think that each is true. Here, empirically equivalent means that the two theories say that exactly the same possibilities empirically, or same empirical possibilities are in fact possible. In other words, if theory 1 is true, then the world will look some way. If theory 2 is true, the world will look some way, and those are the same ways. And there's a common intuition that if two theories have the same empirical consequences, then there's going to be equal reason to think that each is true. And this intuition, comes from the idea that, well, if they both tell us that the world will look some certain way, then by looking at the world and seeing it's that way, I can't tell which of these two is the one that's really there, right? And so the intuition here is that the structure of the theory doesn't matter. What matters is the observation. And the observational stuff alone should be able to tell me which of the theories is true. And so if you think about it for a while, you can see that this goes pretty well with the orthodox view of theories, because there's the theoretical stuff, there's the empirical stuff, they're really splittable. And so when you are asking, take the two different theories that are hovering over the empirical, change only that stuff, and what's the difference? So even though this is a common intuition, it's a common intuition that Clark Gleamore argues against in a paper in 1977. And what he argues in this 1977 paper is that there's a pair of theories, T1 and T2, that satisfy the four following things. First, T1 and T2 are empirically equivalent. Second, T1 and T2 are distinct theories. So here's a case where we have two different theories that are empirically equivalent. Three, or there's no non-empirical reason to prefer T1 or T2, right? So it's not like we somehow know that the structure of reality is such that there must be or must not be molecules, right? We just don't know that kind of thing. All we know is what the empirical evidence is. And so it looks like, if you combine these first three things, that we're in a situation where there must be equal reason to think that T1 and T2 are true. But what Gleamore argues is that in his example, there's a good reason to prefer T1 over T2. And so this common intuition has to be wrong. You can have two theories that are empirically equivalent, but distinct theories, but one of them we have more reason to believe than the other. The ingredients to make this kind of argument, what he needs to do is he needs to give us a notion of empirical equivalence so that we can say the theories are empirically equivalent. Give us a theory of how a theory gets supported by the evidence, and then give us a standard according to which we can say the two theories are the same or distinct. So I wrote these in the wrong order for the structure of his argument, right? What he really needs to do is give us distinct theories that are empirically equivalent and show that one is better supported than the other. He works with an intuitive notion of empirical equivalence. It is a case where I think everybody agrees the two theories are empirically equivalent, and so we don't need a complicated theory about it. He works with what he would later, or what he calls at the time, a bootstrap theory of confirmation. This is a rather extensive theory that's intended to address the third point in the question from the break about falsification. Here is, Gleamore says in his bootstrap theory, here is exactly how one goes about confirming and falsifying theories. Very roughly speaking, his story is, if you want to test a theory, what you do is you add assumptions that let you compute unobservable quantities from the data, and then check if the theory's hypothesis obtains. And so he calls it bootstrapping because you can never, on this approach, test a theory all by itself, because you need to add certain assumptions that allow you to learn things about the theory, which then you check if the theory implies what's going on. And so it looks a little bit like something circular is going on, and many people have criticized it, and when, previous versions of it for being circular. Gleamore argues that it's not circular. Part of what he's up to in this 1977 paper I'm talking about is trying to argue that he has a good theory of confirmation. But for my purposes, what I want to focus on instead is his standard for distinctness for theories. Because he's pretty explicit about the fact that he says the natural thing to do is to use the proof theoretic one that we're all very familiar with. If we have these two theories and they have a common definitional extension, then they are the same theory. They say the same thing. And so if they don't have a common definitional extension, then they're different theories. And so that gives us a standard of distinctness. The problem that Gleamore is aware of and sensitive to is that people don't like the proof theoretic one, in the sense that they think it's not very plausible, but moreover, he wants to talk about a concrete example, and the proof theoretic one doesn't fit with his concrete example because the case he's working with doesn't actually involve models of logical theory, and so he can't use that. But he can still use the model theoretic kind of approach, because he is still working with classes of mathematical structures, and so he says, well, if there's a particular kind of bijection between the classes of models, then these theories are going to be the same. And so I guess the two things I wrote here are proof theoretic and model theoretic standards for theories being the same if they have a common definitional extension, or if they stand in a particular kind of bijection. They're distinct otherwise. The real case that I was looking at in this paper is the case where the two theories of Newtonian gravitation and geometrized Newtonian gravitation, which is a reformulation of Newtonian gravitation in the language of differential geometry. It was developed in part to talk about structural relationships between general relativity and Einstein gravitation on the one hand and Newtonian gravitation on the other. In geometrized Newtonian gravitation, one doesn't have in geometrized Newtonian gravitation, there is temporal curvature, much like in general relativity, there is spatiotemporal curvature. And in both cases, this curvature explains gravitation effects, is the idea. Because I don't want to introduce all of the details about geometrized Newtonian gravitation, I'll just talk about this toy case that he introduces as like a really simplified version of what's going on. So imagine we've got this theory in Gleamore's paper. He says, imagine that you're teaching a student and comes up to you and they say, I've got this great new theory. It's very much like Newtonian mechanics, except Newtonian mechanics talks about force. And I think there are really two things that are relevant, Gauss and Morse. Gauss and Morse are these two different quantities. Neither of them is always zero. And they work just like force when you add them together. And that's all that I can say about them. And so then, the student goes through and they write down their theory. They write down Newton's three laws. An object moves with constant velocity unless it's acted upon by a non-zero sum of Gauss and Morse. When you add up the Gauss and the Morse, you get the mass times the acceleration. If a body acts A, but acts on a body B, then B acts on A with a Gauss plus Morse of equal magnitude but opposite direction. And so what we presented with here by construction are two theories that are distinct because, one of them says there's this Gauss and Morse and the other one says there's just force. They're empirically equivalent because the only connection between the theory and observation in the Gauss and Morse theory goes by way of defining force in terms of them and then seeing what is implied by this notion of force. But Gleamore wants to say, well, the evidence really speaks in favor of Newtonian mechanics and against the Gauss plus Morse theory. This is sort of intuitively right, I think, and he thinks, because he thinks, there's something intuitively right about this. You might want to say something about simplicity or something like this, but what we want is a precise sort of story about what exactly is it about the structure of this case that makes Newtonian mechanics look better than the Gauss plus Morse theory. Yeah, good. So I said it's empirically equivalent. Here's why. You can't measure force directly. You also can't measure Gauss or Morse directly by stipulation. Gauss and Morse only affect measurable quantities like length and acceleration when you combine them by adding them together to give force. And because of this, the data will be consistent with one theory if and only if it's consistent with the other, because the consistency between Gauss and Morse with the data goes by way of consistency with force. And so if it's consistent with the force, then it's consistent with the sum of Gauss and Morse. Okay, so this is, of course, a very silly little theory. The point is that geometrized Newtonian gravitation has essentially the same structure, just in a lot more complicated way. Now, it follows from Gleamore's theory of confirmation that the force theory is better confirmed than the Gauss and Morse theory. And very roughly speaking, the reason for this is that the split between Gauss and Morse is untestable, and something being untestable is bad. If the theory has an untestable bit, then it's bad. This is way too simplified of an explanation of what is going on with Gleamore. One way to see that it's way too simplified is that, it kind of seems obvious. And why do you need the theory to say this? Well, because you need the theory to say something much more concrete in the more complicated case with geometrized Newtonian gravitation. But I want to talk about this case because the places where people have used category theory in philosophy of science have focused not on the theory of confirmation, but rather on the distinctness of the theories. So a model of the Gauss plus Morse theory naturally determines a model of the force theory. You just define force as being the sum of the two. And now we've got a model of Newtonian mechanics by design. That's what the Gauss and Morse theory is designed to do. But this map is not injective. Why? Well, because think about the case where the Gauss is 0 and the Morse is 2. And the force will be 2. But if the Gauss is 2 and the Morse is 0, that's a different values assigned to Gauss and Morse, but the force will be the same. And so these two different models of the Gauss plus Morse theory give you the same model of the force theory. Because this map is not injective, it can't be bijective, and so the theories have to be distinct, using the more careful version of this bijection criterion that Gleamore is involved, is working with. In the case of geometrized Newtonian gravitation, one has a much more complicated version of this kind of non-injectivity. Conclusion, says Gleamore, it's possible for theories to be empirically equivalent but unequally supported by the evidence. In particular, it's possible for realistic theories to be this way because you think, Newtonian gravitation and geometrized Newtonian gravitation exhibit this sort of feature. In 2016, James Weatherall wrote a paper, one of the first papers that explicitly applies category theory to these issues in formal philosophy of science, arguing that category theory suggests a different standard of theoretical difference. So proof theory suggested one standard of theoretical difference, but it was hard to implement that in the cases that we were thinking about. Model theory suggests a different standard of equivalence, and that's the one that Gleamore uses. Weatherall says if you use category theory and the notion of natural identification that I was talking about, then you get a third standard of theory, according to which Newtonian gravitation and geometrized Newtonian gravitation are not distinct theories. So the way that that looks in the Gauss and Morse theory is that says we should naturally identify two models if G1 plus M1 equals G2 plus M2. In other words, they give you the same value of the force. And he said, and if we adopt this criterion of distinctness, then the force theory and the Gauss plus Morse theory are not actually distinct. So, a lot of the work, the philosophical work Weatherall needs to do in the paper is to argue that we really should naturally identify these two models of the Gauss plus Morse theory. And because this is just a toy model, what he really focuses on is arguing that in the case of geometrized Newtonian gravitation, one ought to naturally identify these. And so there, it's really, I think, a plausible argument, one that I think is right. And so at least when it comes to the case of geometrized Newtonian gravitation, Weatherall gives what I think is a plausible argument that the correct criterion of distinctness is the one that's suggested by the category theoretic formulation here. And so one should say that the force theory and the Gauss plus Morse theory aren't actually distinct after all. And so if Gleamore's theory says that one's confirmed more than the other, that's a problem for Gleamore's theory. So argues Weatherall. Let me give a second example. This time the example is empirical indetermination. And one way to motivate this problem is by talking about the so-called whole argument, specifically the version due to John Ehrman and John Norton in a paper from 1987. Models of general relativity are tuples containing a smooth manifold M, a Lorentzian metric G, and some other geometrical quantities. We're going to, if you go look at GR, you find that the Einstein equation is isomorphism invariant in the sense that if Mg is isomorphic to M prime G prime as a Lorentzian manifold, then one satisfies the Einstein equation if and only if the other one does. Corollary, there are going to be some pairs, Mg and Mg prime, where the underlying smooth manifold is the same, but the metrics are different, and these will both satisfy the Einstein equation. If you want to construct one of these, take a bump function on M, convolve it with the diffeomorphism, and then do a pullback. And you'll get a pair of isomorphic Lorentzian manifolds with the same underlying smooth manifold, but different metrics in the natural sense. And these will both satisfy the Einstein equation. So Ehrman and Norton say, well, this poses a dilemma for a certain kind of interpretation of GR. There's actually two dilemmas that it poses. I'm going to focus on one. They call it the verificationist dilemma. we've just seen that there are pairs mg and mg prime, where g is not equal to g prime, and these both satisfy the Einstein equation. These models therefore disagree on which metric properties are assigned to which points, and so they're distinct physical situations. But they're observationally indistinguishable because they're isomorphic as Lorentzian manifolds, and so our ability to tell which situation we're in is going to be limited. And in fact, it's pretty bad because whenever there's a pair like this, there's going to be infinitely many like this. And so for any observational situation, there's going to be infinitely many possibilities compatible with it. And this is at least philosophically spooky, right? So they then say, this problem, maybe not so bad, things do get worse, but in order to talk about the way they get worse, I have to introduce a bunch of other stuff, and so I won't. Instead, what we'll do is talk about a second use of category theory in this context. One way that Ehrman thought, or maybe suggested, that one could avoid this problem is using the notion of Einstein algebra, which is a certain kind of structured algebra of functions due to Garrosh in 1972. Essentially, what an Einstein algebra does is it takes a Lorentzian manifold and then just axiomatizes the sheaf of functions on that in the metric on that Lorentzian manifold. And so it's a way of writing down the structure of the algebra of functions on a manifold without mentioning the manifold directly. Each Lorentzian manifold defines an Einstein algebra, but you can just write down what the algebra is without talking about the manifold at all, and as such, you can write it down without talking about points. Since Einstein algebras, Ehrman argues in 1986 that because Einstein algebras don't mention points, there's not going to be any way for us to get the kind of empirical indistinguishability, because what was, going back to the previous slide, where did we get the distinctness of the two situations? Well, because the models disagree on which metric properties are assigned to which points. But if there are no points, they can't disagree on this, so they can't disagree, and so we get rid of this extreme underdetermination. So suggests Ehrman in this 86 paper, and in a couple of other places. So a second place where people have applied category theory in formal philosophy of science is in replying to this kind of move. So in a 2015 paper, Rosenstock, Weatherall, and Barrett argued that Ehrman's argument doesn't work. Fields end up being equivalent in the way that Newtonian gravitation and geometrized Newtonian gravitation are. Because given an Einstein algebra A, one can construct a Lorentzian manifold Mg whose algebra of smooth functions is A. And so, and moreover, if that algebra of smooth functions on some M prime G prime is A, and then Mg and M prime G prime can be naturally identified. And so not only can you recover a smooth manifold, a Lorentzian manifold from the Einstein algebra, but moreover, it's essentially unique. And so there's, in some sense, no less information in A than was in the Lorentzian manifold that you started with. And so according to this standard of equivalence, Lorentzian manifold theory, the Einstein algebra theory, these are equivalent. And so Rosenstock et al. Conclude, if there's problematic indistinguishability in one case, then there also has to be problematic indistinguishability in the other. In other papers, some subsets of the authors here argue, and there's no problematic indistinguishability in either case. But the place where the place where category theory ends up getting used, or the place that I want to focus on is here by saying, what we've done is we've said you've got these two theories, but they're actually equivalent, and so we don't need to worry about this. Okay, so then let me summarize to wrap up because we're getting to the end of the time. So I think a very nice summary, Weatherall gives a very nice summary in the 2021 paper. Most applications of categories in formal philosophy of science have focused on comparing classes and models using this notion of equivalence. I'm just giving two examples, right? One where the point or the technical core of the argument was a certain kind of equivalence between geometrized Newtonian gravity and regular Newtonian gravity. The second example, there was a certain kind of equivalence between Lorentzian manifolds and Einstein algebras. In both of these cases, the contribution from category theory was in supplying this notion of equivalence on which the rest of the argument was based. This is a general fact about the way most people have used category theory in formal philosophy of science. They have imported this notion of equivalence to the model theoretic approach. They've done different things with it. So sometimes these equivalences are used to make a positive point about the structure of scientific theories, like, say, in the discussion with Gleamore, or to try to deflate a metaphysical position, which is the kind of ultimate aim of the discussion about general relativity. The idea here to be that whatever else is the case, these mathematical formulations can't capture a metaphysical difference that you might be interested in. That's a kind of positive use of these notions from category theory. Another kind of discussion people have, though, is how exactly you ought to use this notion of equivalence, whether it actually captures something interesting, whether it's too weak, too strong. I mean, most people think it's too weak. That's a kind of internal negative discussion point of it. But in either case, most of the focus has been on using this notion of equivalence in the model theoretic approach. And as Weatherall indicates in this paper from 2021, while, you know, it looks like there are various research programs that one might pursue here. Let me, as just a very brief parting thought, say something about my own attitude about this particular question about how to use category theory in this case. So I think that the successes of the model theoretic approach, historically speaking, they came from replacing the proof theoretic approach by saying, no, the proof theoretic approach got something wrong in this case. It got something wrong about the structure of explanation, or about how one captures or delineates the empirical content of the observable content of the theory, or about the confirmation, the structure of confirmation in the theory, something like this. You know, explanation is not deduction, predictions are not deduction. Instead, they're this more complicated model theoretic thing that we're going to have to disagree about. But, you know, at least model theory is providing a kind of inspiration for things one could do here. It seems to me that so far, for the most part, the category theoretic approach, or really uses of category theory in formal philosophy of science, have mostly been used to add to the model theoretic one. In the two examples I just gave, what's been added is this new standard of equivalence. And I think that some of the problems that this category theoretic approach Yes. I'm so sorry. Great, sure. Yeah, so the last thing that I was saying, just as a point of wrapping up, I wanted to give two concrete examples of things one could do with category theory and formal philosophy of science, as a kind of indication of, you know, starting points, right? Kinds of where can we go from here? So there's a paper from 2021 by James Weatherall that I think very nicely summarizes the kind of situation with category theory in philosophy of science at the time in 2021. So interesting things have happened since then, but I don't think they've gotten written down in a general way yet. Sorry, one second. To try to summarize what the landscape looks like in formal philosophy of science with category theory being applied, one might say that most applications have focused on comparing classes of models using this notion of equivalence that I've been talking about. So in both the Gleamore case and the case of confirmation and the case of empirical indetermination, what people did was they brought in category theory to say these two theories are equivalent with respect to this standard of equivalence, and therefore some philosophical consequence will come. This is a general pattern that can be reused. You can use it in other cases, and it has been reused in other cases. Right? You can try to use these equivalences to make a positive point about either the structure of scientific theories, or another place where it's often used is to try to defeat a certain metaphysical position. People will apply it to say, well, look, you've got these two metaphysical positions. It looks like here's how you could formulate them mathematically. Let's then have a debate about which mathematical formulation is more perspicuous. One kind of argument says, no. If you're careful, you'll see that these two mathematical theories are in fact equivalent, and so you shouldn't try to distinguish them because you're going to fail, right? You're going to end up seeing differences that aren't real. So that's one kind of if you like, positive use of this notion of equivalence, or it's positive use of category theory in these cases. It's taking results and then trying to apply them. A second way that the discussion has gone has been trying to pin down what exactly one can say about this notion of equivalence in the model theoretic context. Because, as various people like, say, Hans Halvorsen and Thomas Barrett have shown, Lawrence Hudetz, there's lots of sort of cases where we have the two things that are equivalent according to the standard, but intuitively one wants to say that they're distinct, or intuitively some people want to say that they're distinct. And so this is something of a negative or critical part of the literature in category theory and philosophy of science. Is trying to understand, what exactly are the limitations or applicabilities of this notion of equivalence. And so I think this 2021 paper from Weatherall does a really nice job of laying out both the successes and the puzzles of this kind of program, and indicating various possible future research programs along these lines. To wrap up, I wanted to just say one thing about my own views here, which is that, as an observation, the successes of the model theoretic approach, I think, came mostly from replacing the proof theoretic approach, or cases where it replaced the proof theoretic approach, right? Getting rid of the analysis of the observable theoretical distinction in the proof theoretic approach and replacing it with a different one. Getting rid of the understanding of explanation in terms of derivation and replacing it with a different one. Getting rid of the picture of falsification in terms of deriving observable consequences and replacing it with a different one. And in all these cases, I think replacing it with one that is more philosophically sensible and closer to scientific practice. But the category theoretic approach really has not exactly been a category theoretic approach so far. Mostly what it's been the model theoretic approach enriched with certain concepts from category theory, primarily this new standard of equivalence. And while I think that there is something right about this, and that the two examples that I just talked about do get at something correct, I do think that some of the problems that this approach ends up facing come from trying to combine these two different perspectives on the class of models, right? By trying to import ideas from category theory into the model theoretic approach, you end up saying things that I think lead to problems and that people have recognized as problems. And my own attitude is that the way to address these problems is to use categories more extensively, right? One should, when you see these problems, don't say, oh, well, the problem is that we're trying to use these category theoretic concepts and those are bad. No, the problem is that we're trying to use these category theoretic concepts in the old model framework, when instead we ought to see that there's a conflict and then not use the model theoretic one if we're going to understand what the category theoretic one is doing. We should try to compare these approaches sort of on their own terms rather than trying to mush them all together, if you like. So then finally, I would say you, and I'm very happy to discuss mathematical philosophy and category theory in formal philosophy of science in particular over email, and so you should feel welcome to send me one. Yes. I remembered that as soon as I waved, I then remembered, no, that's what that, yeah. Anyway, thank you for mentioning these. Cheers. Yes. Yes, let me, oh, you know what? Sorry, 1 second. I think uh, that's probably the best option. Yeah. Yeah, that is a good question, and I think it's interesting the way that historically things kind of go. So it's funny, right? The kind of, I think, natural first thing to say, if you're familiar with these, is to say, well, hold on, soundness and completeness means that these two will be, there's no difference between the two, right? In practice, because anything you can say with one, you can say with the other. Now, historically, I think people went, I think, the wrong way in executing this kind of debate, right? So one thing that people will point out is, well, soundness and completeness is all well and good, but there are still going to be sorry, I'm forgetting the terminology for non-axiomatizable classes and models. Non-elementary classes, is that it? Abstract elementary class. Sorry. I'm a little tired, but the point is just there was some sort of thread of debate that says, well, no, look, because even though there is going to be a certain kind of coordination that's possible to do between the two of these, there's going to be things you can say in one that you can't say in the other. My own attitude is that if you're careful and if you see the way things are going, if you're careful about what you're doing, it must be the case that you can say anything in one that you can say in the other. That just seems to be, by design, what one is doing in proof theory and model theory is trying to make the proof theory and the model theory match up appropriately. And the interesting question is not in mathematical logic. The interesting question is not, do we have soundness and completeness? That's sort of something that one designs the theory to do, but rather make sure that we have soundness and completeness to make sure that we're in a reasonable sort of situation, and then ask sort of further questions. That's an oversimplification because sometimes one does care about soundness and completeness, but not in ways that bear on philosophy of science. I think that if there is going to be a difference between the proof theoretic and the model theoretic approach, it has to be a different. And this is on the one hand a little sorry. Okay. Yeah. Maybe I'll just pick up with the. So there was this whole fight between the two of them about whether you can say one with something with one that you can't say with the other. And that fight's still ongoing. And my own attitude is it better work out such that you can say anything with one that you can say with the other. Because being able to say something is a very minimal kind of ability. With enough work, you know, you can encode anything in just binary, and there you go, right? Why bother, you know, doing anything? Just use binary to represent scientific theories. Well, you don't want to use binary to represent scientific theories because the point of having a representation is to make it easy to work with. And so if there's going to be a difference between the two, it's going to have to be a difference of orientation, of strategy, of what's salient in one compared to the other, of what's easy to say in one rather than the other. And I think that this is the kind of thing that unfortunately one's not going to be able to delimit by some kind of, you know, you can't prove that you can't do one thing, something in one you can't do in the other. I think in the case of category theory, you get similar kinds of debates about can you do things with category theory you can't do with the other case. And I think that that's, I mean, my own attitude is that's the wrong way to go, because what was actually profitable or compelling about the kind of semantic view was the natural way of picking out, say, the observable substructures is not the natural way of picking out the observable substructures on the proof theoretic approach. And so, yeah, is one fundamentally different? I don't think so, because fundamental just means add whatever you need to make them the same. Are they different? Well, I think so, because people disagree about which one's natural. So, you know, it's not, yeah, I don't know. That's the answer for that I have. Yeah, so this is, I think, to me, an extremely interesting question, and one that I think requires or deserves more attention. So my own sense of the way people think about this is that I said, what does the model theoretic approach do? It says, well, the theory is a class of models. Now, as a first pass, this is, I think, what the approach says, and it's what people say. That's the slogan version of it, right? But if you, the next question is like, well, okay, what does it mean to say that the theory is a class of models? And here, I think the answer has to be something like, well, when you want to ask questions about the internal structure of the theory, then you're going to need to do various kinds of model theoretic constructions. So, for example, to take a really simple example, you know, I've got the whole class of models of the theory, and I want to know, well, you know, what does the theory say about situations where, let me take Newtonian gravity just for simplicity's sake, right? I've got this whole class of models in Newtonian physics, all the different possible physical systems that can be described by Newtonian mechanics, and I want to know, okay, well, what are the possibilities for a little island solar system, just a little sun with the planets moving around it and nothing else in the universe? The model theoretic view says, oh, well, that's easy. You take the subclass of models that only have a solar system and nothing else done. The proof theoretic model approach is going to say, well, take the class, you know, add to your theory the statement that there's only the one solar system in the middle. Here's a case where I think they're going to work out to be, say, the same kind of thing. The category theoretic one, I think, says something different, but that's getting far afield. So if you want to talk about the internal structure of the theory on the model theoretic view, what you need to do is you need to articulate a certain kind of model theoretic construction directly in terms of models that will pick out the internal structure. And I think that this is something that is so natural that people haven't really worried about it, right? So in the case of, say, distinguishing the parts of the theory that are directly or more directly on the periphery, more directly confronting the tribunal of experience, distinguishing those from the internal stuff that's more immune. This is going to be on the model theoretic approach involving a chain of models whereby we have sort of the theory of Newtonian physics, say, the theory itself is going to be the core parts of the theory, or if you like, the set of models that are compatible with that are the theory, are going to be actually pretty far from observation, because if you want to talk about how to connect Newtonian physics to observation, you need to, on the one hand, you need to do what Newton does in the Principia in the beginning, when he's listing the phenomena about the Jovian satellites and the Saturnian satellites and so forth. You need to come up with data models, right? You need to turn the data into a particular kind of model and then ask, okay, how does that data model fit with my model of the experiment? How does the model of the experiment then fit with the model of the Newtonian theory, right? And this, if one's more careful, one will see that, of course, really there's going to be more and more chains of models. And so if we want to have a kind of more holistic quantity picture, what we need to say is, well, there's going to be kind of the class of models that is our entire theory, and that's going to be huge. And then within that, there's going to be smaller classes of models, like the class of models in Newtonian physics. And that's going to be, that class, the smaller class is going to be relatively insulated from observation, because in order to connect it, you have to use this big long chain where you go by, models of the experiment, data models, et cetera, to get out towards the end. And so the way that the model theoretic kind of approach is going to articulate the idea of inner or insulated parts of the theory is by saying, well, there's going to be chains of models. And this chain, the length of this chain is what is capturing this spatial metaphor here of being inside. Yes, I can hear you now. Ah, that's very clear. Yeah, now we're good. Yeah, great, good. So I mean, this is a great question. I mean, this is something that I worry about, and there's a couple of things I want to say. So like, maybe I'll start with the kind of flat-footed answer. So much of what I was saying today, I take to be kind of a report about what this literature sort of thinks it's up to. So I'm part of this literature, and so to some extent, I also think that something like this makes sense. But like, there's definitely, this is, I think this is a hard question. I think not everybody does think it's a hard question, but I think it is one. The reason that some people think it's not a hard question is because they think, look, probability theory. What's that? Well, that's the theory of measure spaces. What's the theory of measure spaces? Well, it's a theory about a certain class of structured sets and maps between them, measurable maps. And look, I've got this semantic theory, I've got this model theoretic view whereby I can talk about classes of models, and so if your models are probabilistic, then there you go. It's just got measure spaces in them. And so there's nothing to worry about. I personally don't find that answer particularly compelling, and I don't find it compelling for reasons related to my answer to the what's the difference between the proof and model theoretic approaches, right? The fact that you can say something in there isn't, I think, for me, quite enough. In particular, the kind of, so you know, I think that that's like a concrete case of the more general worry that you were expressing, right? Which is a kind of rigidity, and I feel like softness is maybe the right way to put it. This is a problem that arises on sort of every approach, right? So in order to talk about in the proof theoretic case, one has to talk about a language, and that language has certain terms, and these terms have a particular extension, and that means that the meaning of the term can't sort of evolve over time. But like clearly that's not the way things really work, right? Like you listen to radios now on the internet, but those aren't being transmitted via radio waves anymore, so they're not really radios, right? But no, that's just because language evolves in a certain kind of way. And so one kind of answer is, well, I'm idealizing in various ways, and so in particular in the temporal case, I'm taking like a snapshot, and I'm also pretending that there's no open texture here or softness to the bounds of the terms, but really there is, and a full story is going to have to tell how you de-idealize, and that's going to be something maybe along the lines of that chain of models that I was talking about. There's going to be sort of rough fit between going all the way out. I mean, it's not clear to me that that's really actually going to work, and I think that this is a very difficult problem and an interesting one, both because it poses difficulties for these kinds of formal treatments of philosophy, of scientific theories, but also because I think it poses similar problems for natural science, modeling in natural science, and mathematical model in natural science, right? Because, you know, if you want to compute something, you got to compute a number. And that number is going to have some number of decimal places after it, limited by your computation, your floating point arithmetic, right? And of course, you don't want to say that, oh yeah, I believe there are, like, your number is exactly right out to every place that I have calculated or something like this, because you think your model is going to break down at certain scales. And so what one wants is some way to say, like, yes, I've got this really rigid model. Yes, this rigid model says some stuff about my target, either in formal philosophy of science or in scientific modeling. Yes, I think I'm getting some information from this formal model that I've devised, but no, I don't think that, like, somehow my model has rigidly captured the exact outlines of what I'm talking about. So I think that it seems to me that one does have to have this kind of softness that you're talking about, not only in this context, but also in modeling contexts in natural science. And I think that kind of softness is under-theorized in the literature that I'm discussing. I think there are places where people try to talk about it, but not. That's a good question, and I would like to think more about it. Bye. Thanks very much. Nice to meet you all.